Again, 7 points each. Nothing but hundreds here, right, folks? Of course.
No, wait.
What? No. Folks, questions on the homework? Yes. Number 20. Folks, listen up. I'm sorry, because of what now? The graph of G can be obtained by reflecting the graph of F on the y-axis and shifting 3 units to the right.
Yeah, I just thought it so.
The way that it's written with the negative x plus 3, and unfortunately that would be more like 10 times negative x minus 3 with the negative on the outside. I'm not going to try to trick you up with anything like that, folks.
When it reflects over the y and moves to the right.
No, this is going to be a reflection over the y, correct. The reflection over the x would be something if it was in front of the 10. But yeah, reflection over the y, and then a shift. If anything, that would probably be more confusing than the one. So this is the stuff that we did look at yesterday, graphing the logs, graphing the exponentials. We graphed quite a few of the log functions, talked about them. But today we're going to go, hopefully just a review on what is logarithm function with base A. So, for x greater than 0, a greater than 0, a not equal to 1, we have our y equals a logarithmic function with base A of x, if and only if x equals a to the y. One of them we have it written in log form, logarithm form, the other in exponential form. So when I have the logarithmic form, and I'm looking for my a, my x, or my y, I can express it in exponential form and go ahead and solve the way that we know how to solve any particular equation. So the function f of x equals logarithm function with base a of x, it's just that. Logarithmic function with base a of x, or better yet, just log base a of x. So we always want to state what is that base and what is the particular x we're looking at. You're not hearing me say that logarithmic function with base a of x, again, it's log base a of x. So using that information as far as going from our exponentials to our log form to our exponential, Here we want to write the log equation in exponential form. Log base 4 of 64 equaling 3. So again, here we're taking a look. We have that log base a of x, and we want to write it with the x equals a to the y. My base of my exponential is the same as my base of my log. And then what do? We just go across the equality sign, giving you a to the y, and then back through the equality to give me that x. So over here, we have log base 4 of 64 equals 3. So we want to start off with what base? 4. And then what? Going across equality to?
3.
So 4 to the third equals? Absolutely. So these two express the same thing as far as one's just in exponential form, one's in log form. Log base 4 of 64 equals 3 can only happen when 4 to the third power equals 64 and vice versa. So for part B, Alejandro, we have that log base 7 of 1 over 49 equals negative 2. So again, starting off with the base. Our base is 7. And then going across equality, there's a lot of convolution. And coming on back? Absolutely. That's all we're doing, hopping back and forth between the equality sign to come up with an exponential. So log base 7 of 1 over 49 equaling a negative 2 only happens when, of course, when 7 to the negative 2 equals 1 over 49. All right? We can go the other way as well. From the exponential equation, write it in log form. Starting off with Dallas. 5 to the third equals 125. So again, what is the base we're dealing with? So I have my log base 5. Absolutely. Of 125 equals? Absolutely. As Dallas said, starting off with the 5, and then going across the equality sign and coming right back. That's how we come up with our log form or our exponential form. My log form, it's always asking, on the other side of the equality, it's always asking for what? It's always asking for the power, the degree. What power do I raise this number to get this other number? So you're always asking on the right side of your log function, what is that power? So for the second one, Nicole, we have 81 to the 1/4 equals 3.
Is that equals 60?
It should be down.
Log 81.
Log what?
81.
Base 81. So log base 81. There's no time here. Log base 81. How do we say it? Log base 81 of 3. Absolutely. Absolutely. Log base 81 of 3 equaling 1/4. Again, the log expression on the equality side is always asking for that power. Yes, sir. Right. -4 would be an equivalent thing. 1/4 is what we're looking for. Questions? All right. So, just using the basic definition or the using our one-to-one property, we can also solve equations like this. So, or just the basic definition of what a log is. So starting off with Dominic. Here we have log base 4 of x, or f of x is log base 4 of x, and we want to evaluate it with x equals 16. So we're looking at log base 4 of 16 equals what? Some number, my y. So how do I write this exponentially? 4 to the y equals, so I'm looking for that unknown y, so 4 to what power gives me 16? 2. Absolutely. So as Dominic said, we come up with my f of 16, then it's going to be a value of 2. Because 4 to the second power equals 16. That one? Here we have for b, log base 2 of x, where x equals 64. So what are we asking? again, the log function is always asking for what? What power, what degree? So we're saying 2 to what power gives me 64. So we come up with a value of 6. Okay. Again, it's a lot easier to take that log form, log equation, and write it in exponential form, and there to determine what is that missing value. Log base 5 of x, where x is 1, and we're asking for log base 5 of 1.
And then it'd be 5.
5 to the y, okay.
Y equals 1.
All right.
Y equals 0.
Absolutely, absolutely. Skill said there's only one exponent I have, where I'm going to wind up with a value of 1, and that is where y is equal to 0. So here, that log base 5 of 1 is equal to 0. And lastly, Dorian. We have that log base 3 of x, where x is 1 over 81. You get a fun one there? That's all right. If we write it in exponential form, as Dorian said, we get 3 to the y equals 1 over 81. But they don't have that same base, so you can do that. What do I need to do? Okay, so how can I match it then? Can I express 81 as 3 to some power? Power. So 3, 9. Absolutely, 3 to the 4th. We're not quite there yet. What else do we need to do now? Because I need them to be on the same base. So how do I bring that 3 onto the top? Using s y equals -4 due to the 1-to-1 property. So just like we did before, using that 1-to-1 property, right, if I take that same base, and this is what we come up with. Questions? Again, this works for all my logs, whatever that base is, transforming into our exponentials. We do have certain bases. One of them, which we talked about before, the common log. Common log has a base of 10. Denoted by that log base 10 of x, or the majority of times we just see it as log of x. The common log, again, very rarely will you ever see it written with base 10. Whenever you do not see the base for logarithm, it's understood as common logarithm. Right? So, let's take a look at some of these calculations. So we want to use a calculator to evaluate our common logarithm at each of these values. So here, first things first, find that common log of 10. So we can use our calculators. And where is my log? Absolutely. So here's my log. And it's a common log, so again, that's our understood base 10. What are we going to get? I'm sorry? So here we come up with, here we didn't even need a calculator because it's, again, it's asking us 10 to what power gives us 10. Of course, that's just going to be 1. For the part B, Kyle. Let's see, we're looking for that log. Common log of 1/3.
-0.77.
Does that sound right? Does that answer make sense? Why is it negative?
Oh, because it's a fraction.
What's that have to do?
Less than 1.
Okay,
It's, yeah,
so because it's less than 1, that's why it's negative?
it's greater than 0. It's because it's less than the number 2. It's less than 10.
All right, consider it. What does the graph of this look like, folks? What's the graph of our log function look like? What is that intercept?
1, 0.
So anything to the left of my intercept, what y values does it have? Negative values. The closer and closer I get to that 0, of course I'm going to have very large negative values. So of course, that does make sense having that negative value. So do not be thrown off by having negative positive values. Ask yourselves, okay, I know what the graph looks like. This does make sense. So, what about that 2.5, Solani? Our common log of 2.5. What's that? I'm sorry.
0.
Okay, pretty much 0.398-ish or so. And so,
Well, that would be it's impossible.
why is it impossible?
You have an asymptote at x equals 0.
So what does that mean?
It's not in your graph. It's
Not in my,
domain.
absolutely, as Sean said, it is not in my domain. We do not even need to use a calculator. What is the domain of my log function? 0 to infinity. Negative 2 is definitely not in that domain, so it does not exist, right? Don't just go with the calculator telling me error, so I did something wrong. No, it also knows it's not in the domain. However, it's not going to tell you this is not in its domain. And that's for you to remember, what is my domain, what is my range? Is this a valid number, a valid input to get as far as our calculations? So, with our log sum, with our common log functions, or any of our log functions, we have certain properties that make it easy. So one of them, log base a of 1. So I'm saying a to what power is going to give me 1? Absolutely. So anytime I have log base of a, doesn't matter what that a is, of 1, I'm always going to wind up with an answer of 0. Secondly, log base a of a, again, a to what power gives me a? Absolutely. I'm going to get 1, excuse me, I'm going to get my one I started with, I'm going to get that back when I just raise it to the first power. And then we also have log base a of a raised to the x, along with a raised to the log base a of x equaling x. These are called my inverse properties. So whenever I see the base matching up with that a to the x, it's pretty much all this is just disappearing. Right? Likewise, if I have that same a and that same base here, all that just disappears, and I'm left with just that x. And lastly, if I had two logarithms with the same base, log base a of x being log base a of y, it's the same thing as 16. Absolutely. if I have the same base and I have the same log, I'm just ignoring the logs and it's just x equals y, and this is just my one-to-one property. So using these properties, we can easily evaluate some of our log problems. So here we want to simplify log base 5 of 1, this one. So again, we're asking ourselves 5 to what power? So again, if I want this to equal x, 5 to what power equals 1? Absolutely. Again, anything raised at 0 power is going to give me 1, so it's definitely 0. For part B, Caden, we have log base square root of 11 equals square root of 11. Square root of 11 raised to what power gives me back square root of 11? Absolutely. Again, that's that property right here. Log base A of A is always going to equal 1. And then for part C, Emily, we have 8 to the log base 8 of 30. This is one of my inverse properties. So what do we wind up with? What cancels? All this just disappears, doesn't it? Absolutely. Since I had the base 8, and I have 8 raised to that log, all those just disappear, and I'm left in this case with just 30. Those are just your properties of logarithms. Quick and easy. Then we can also use the 1-1 property. We have log base 5 of x equals log base 5 of 16. Do they have the same base? So due to the 1-1 property, I can just say what then? Absolutely. X equals 16. Since they have the same log base 5, I ignore the logs, I ignore the bases, and just set everything else equal to one another. Aubrey? For the second one here, we have the common log of 4 minus 3x equals the common log of x plus 2. So what do I do?
Step 4 minus 2.
Absolutely. Since I have the same log, same base, she said we set that 4 minus 3x equals x plus 2.
I had a question about a problem before.
Okay, let's finish up this one. So, what do we do now? Solve for x, right? So I'll combine my like terms. 4x equals 2, 4x equals what problem? Okay. And for this last one, Alex?
We're going to set x squared plus 4 equal to 29.
Absolutely, since we have the same log with the same base, x squared plus 4 equals 29.
Make it x equals
Subtract 4. Absolutely, x equals plus or minus 5. How was that, folks? Easy stuff, difficult stuff. Review, hopefully. So, using the common log, again, base 10 is a very common one. It's a common log. There is also another base that is used quite a bit, and that's our natural base, our natural base of e. For the inverse function of our natural exponential function, e to the x, denoted by you will not see, very rarely will you ever see it written as log base e. Instead, you'll see it written as lowercase l, lowercase n, x. And this is just, again, written as my natural logarithm, natural log of x. Or mostly, a lot of times you actually just hear it with the letters said ln of x. So if you're saying the letters ln of x, natural log of x, they mean the exact same thing, log base e of x. So, they're using the calculator. We'll have James help us out, and then Maddie. So, coming up with the natural log of 2. Do we want to use that same button? No, we actually do have specifically for that natural log. So our natural log of 2, what do we get, James?
0.69.
0.693, absolutely. Natural log of 73.25, maybe? 4.294, yes. What type of number are we going to get for C? Negative. And what do we get, actually? As Alex said, since it's 0.4, we know we're in between that 0 and 1, which is below the x-axis. Negative 0.916. Yes, no? And then a very difficult one, just like for the log, it doesn't matter what our base is. Right? It does not matter if I have log base e, my natural log, log base 10, my common log, log base 500. Right? My domain is always going to be between does not exist. My logarithm is always going to be a domain from 0 to infinity. So any negative inputs do not exist. So, properties of our natural logs. Just like we have properties of our logs, we have them for the natural logs as well. Nothing changes other than the way that it's noted. Natural log of 1. What does that equal?
0.
0. Because it's saying e to what power gives me that 1? Okay, that's going to be e to the 0. And then we also have our natural log of e. Again, my understood base of e. E to what power gives me that e? Of course, that's going to be 1. And then my inverse properties. Natural log of e to the x equals x, absolutely, and e to the natural log of x equals x, absolutely. And then our one-to-one properties, what does that look like? Natural log of x equaling the natural log of y implies again, nothing new here, folks, other than now we're writing it down using the natural log. Again, all it is log base e. It's the exact same properties. So using these properties, Harrison, we have natural log of e to the 1/3. Which property are we using there? Natural log of e to something. Natural log of e to the x equals x. So here I have natural log of e to the 1/3. This would just equal, absolutely. Is it saying e to what power? Excuse me, e to the, yeah. It's asking e to what power e to the 1/3. I'm getting confused now. What's it asking, folks?
Not sure why.
To come up with 1/3.
I don't know, just in this stuff, taking math, so let's just stop and take a breather for a second.
Okay. We'll just go to side E then. Side E. For part B, e to the natural log of 8, what are we using here? Absolutely, we're using our other inverse property, e to the natural log of x. Absolutely, so again, all these just disappear. And I come up with 8. And that leaves Chris with the last two. I only had 1 stick left, so. So 15 times the natural log of 1. So 15, what is the natural log of 1? Absolutely, with that first property, we know the natural log of 1 is 0. Absolutely. And for D, we have 1/6 times the natural log of E. And what is that natural log of E? Absolutely. Absolutely. Winding up with that 1/6. Exact same thing with the common log, log base 3, log base 7, but it's just log base E and we write it as ln. Thanks. Questions, folks? Hopefully all this has been reviewed, so that whole entire quiz will be nothing but a review, right? And hence our test on Tuesday. There's no graphing here.
Yeah.